In the last two videos, we developed a simple flight model and HUD, but besides flying the plane, there's nothing else for the player to do. In this video, we will add weapons and an AI for the player to fight against. The AI will have all of the same capabilities and limitations as the player. Its plane will have identical stats and it will use the same weapons. The AI will be simple, but still able to shoot you down. It will be capable of aiming and using its weapons, dodging attacks, avoiding the ground, and maintaining a reasonable amount of energy. The planes in this demo will have two weapons, cannons and missiles. The planes also need a health system. We aren't going to have a detailed damage model like in War Thunder. The planes simply have 100 hit points. When the hit points are reduced to 0, the plane is destroyed. Cannons and missiles have one thing in common. Since they are physical objects traveling at a finite speed, they must lead their targets. For cannons, the pilot must provide the lead by aiming the nose ahead of the target. For missiles, the pilot locks onto the target and the missiles will guide themselves to it. In both cases, we use this code from wiki.unity3d.com to calculate lead or interception. This code calculates the lead needed to hit a moving target, given the speed of a projectile. A few elements need to be added to the HUD to allow the player to use weapons. These are the target box, the missile lock-on indicator, the cannon reticle, and the target and incoming missile arrow. The missile lock and cannon reticle will be described later. The target box is easy. It's a box placed on the target. The position is calculated using the camera.world-to-screen-point function. This box makes it easier to see the target at long range. It also shows information about the target's name and distance. The player should know roughly where the enemy is even when they are off-screen, so the HUD has an arrow that points to the enemy. There's another arrow for missiles that are launched at the player. These arrows rotate around the HUD to point at the target. We use the world-to-screen-point function to place these arrows. When the target is on screen, this function returns a vector 3 where the X and Y axes are both in the range of 0 to screen size. If the target is off screen, at least one of these axes will be outside that range. We can simply calculate the angle from the center of the screen to the returned position to find the angle for the arrow. We can tell when the target is behind the player by looking at the z-axis of the returned value. A positive value means the point is in front of the camera, negative means behind. The view frustum of a camera is commonly shown as a truncated pyramid. Any position in world space that falls inside the frustum can be seen on screen. However, the projection matrix can be applied to any position, not just those within the view frustum. That includes positions just outside the view frustum, like the off-screen target. It also includes positions behind the camera. The view frustum can be thought to continue behind the camera as a second truncated pyramid. Positions that fall in the second frustum will be mapped to similar positions in front, except the X and Y axes are mirrored and the Z axis is negative. So if the Z value is negative, we need to move the arrow to a different rotation. We could simply correct the screen position and calculate the new angle. However, it is equivalent and easier to simply add 180 degrees to this angle. Now as the player maneuvers and turns their camera, the HUD shows where the enemy plane is at all times. The cannon is simple. The plane spawns a bullet which travels forward and damages the enemy plane. There's a line renderer attached to it to act as a tracer. Since cannons can fire a lot of bullets quickly, it will take multiple hits to shoot down an enemy plane. Bullets are small and fast, so they could potentially tunnel through an object. That is, they would pass right through without detecting a collision. To avoid this, we don't use physics colliders at all. Instead, all collision detection is handled using raycasts. Each frame, the bullet raycast from its last position to its current position. If the raycast hits a plane, it applies damage. If it hits the terrain, the bullet is deleted. The bullet is also deleted after traveling for some time without hitting anything. Bullets inherit the velocity of the plane that fires them. This means their trajectory depends on both the muzzle velocity of the bullet and the current velocity of the plane. We use the first order intercept function to calculate the lead needed to hit the target. The result is a position in 3D space which is somewhere in front of the target. To call this function, we need the position and velocity of the firing plane, the speed of the bullet, and the position and velocity of the target plane. This function does not account for drop from gravity, but cannons are generally used at ranges where this is negligible. The lead is displayed to the player as a reticle on the HUD. The reticle simply uses world to screen point again to display the location of the lead position. The player needs to align the bore sight with this reticle to shoot the enemy. The AI will aim at this point when it uses its cannon. Before you can launch a missile, you have to acquire a missile lock. The main limitations for locking on are range and angle. The target has to be close enough and within some angle of the front of your plane to lock onto them. This code is part of the plane class and determines whether the target plane can be locked onto based on those factors. If the plane is in range, then we can begin locking on. We want the lock-on to slowly move towards the target, so we add a variable called missile lock direction that stores the current state. If the target is within an acceptable range and angle of the plane, the missile lock direction is rotated towards the target. Otherwise, the lock direction is rotated towards the default position in front of the plane. When missile lock direction points directly at the target is locked on. The progress towards locking on is visualized by the circle on the HUD. This follows the angle of the missile lock direction and covers the target when a lock-on is achieved. Once the missile has a lock, it doesn't need to be precisely aimed since it has its own guidance. It will calculate the lead needed to reach the target and steer towards that. Missiles deal damage with an explosion, so a direct hit is not needed. As long as the missile explodes close enough to the target, it will deal damage. Real missiles have energy just like the planes that launch them. They need a minimum airspeed to maneuver and lose energy from maneuvering and from drag. Real missiles only contain a few seconds worth of fuel, and once that runs out, it spends much more time gliding towards the target until it runs out of energy. However, to keep things simple, we won't design our missiles to work like that. These missiles won't have to worry about energy or drag. They will always fly at a fixed speed. When the missile runs out of fuel or misses the target, it simply explodes. The missile uses the first order intercept function to calculate the lead needed to intercept the target. We pass vector 3.0 as the shooter velocity, and the missile's speed is passed as the projectile speed argument. The velocity of the launching plane doesn't matter in this project since the missile always travels at a fixed speed. If we did set this parameter to the velocity of the missile, the lead function would behave as if the missile is traveling at twice its actual speed. This would cause a serious underestimate of the lead needed. That causes the missile to act as a tail chaser. It goes to where the target is instead of where the target will be. This would drastically reduce the missile's accuracy. By passing the missile's speed only to the projectile speed argument, we get a proper interception course. The missile knows where it is at all times. By subtracting where it is from where it isn't, it obtains a difference or deviation. We normalize this deviation to find the target dir. This is the direction it needs to face in order to intercept the target. The missile will rotate to face this direction over time. Current dir is the direction the missile is currently facing. If the angle between current dir and target dir is too large, the missile loses the target and explodes. This can occur if the target plane successfully dodges the missile, in which case it explodes a harmless distance away. However, if the missile successfully intercepts the target and passes it, the angle will quickly approach 180 degrees, causing the missile to explode right next to the target. Missiles also use raycasts to check for collision with the ground. If the target is within the angle limit and the missile has not hit the ground, the missile will continue steering itself. Instead of defining turn rate in degrees per second, we can define it by a max g-force. So we can design the missile to have an 8g turn, for example. We can calculate the turn rate in radians per second based on the g-limit and the missile's speed. Note that while the plane is also limited to 8g turns, it can still outturn the missile in many cases. This is because the missile is much faster and thus has a limited turn rate and a large turn radius. Finally, we set the speed in the direction the missile is facing. This means the missile will always move at the same speed. It doesn't lose energy from turning or from drag. The missiles should pretty much always score a hit on a cooperative target. I've set the missile's damage to 50%, so 2 hits are needed to shoot down a plane. The HUD shows when a missile lock is acquired by turning the target box and missile lock indicator red. When a missile is fired at the player, the entire HUD turns red and another arrow appears that points to the missile. This lets the player know where the missile is coming from so they can dodge it. To support this, the missile calls the notify missile launched function to notify the target that a missile was launched. This is of course not something a real missile would do, but this is necessary for the missile warning to work in our game. The planes in this project now have quite a few systems to manage. Despite this, the AI can be a simple state machine while still displaying some interesting behavior. There isn't anything complicated like pathfinding or action planning. Simple checks and rules are enough to have an AI that attacks the player, dodges attacks, and avoids crashing. The main scene has one AI plane for the player to fight. The player can also enable the AI on their own plane to see an AI versus AI fight. The AI's main goal is to point its nose at a target. The target may be the position of the player's plane or any other position in world space. This one behavior is what drives most of the feeling of a dogfight. When the player is behind the AI is constantly turning to get behind the player, which has the side effect of dodging the player's attacks. The steering function starts with the position the AI is aiming for. This position is transformed into the plane's local space. The position of the two planes in world space doesn't matter. Steering is calculated based on the relative direction of the target and local space. The orange arrow shows the direction from our plane to the target plane. We then flatten this direction onto each of the XY, YZ, and XZ planes. Since we are operating in local space, we flatten the vector simply by setting one of the axes to 0. This will produce 3 new vectors. These are used to find the error between where the plane is currently pointing and the target direction. Let's consider a case where the target is off to the side. These directions are shown with the red, green, and blue arrows respectively. The target direction is flattened onto the YZ plane to get pitch error. Then the XY plane to get roll error. And the XZ plane to get yaw error. The difference between pitch error and the forward direction determines the angle to pitch up or down to point at the target. If the target is directly in front, the angle is 0, so the plane receives a pitch input of 0. This is essentially the P term of a PID controller. If that angle is a large pitch down, it gets converted into a pitch up maneuver. For example, if pitch up threshold is 15 degrees, then when the target is more than 15 degrees below the AI plane, the AI will always try to pitch up. If the angle is less than the threshold, it will pitch up or down normally. This avoids situations where the plane would try to pitch down by a large amount, which would result in a slow maneuver from the negative G limit. The same general logic is used for roll and yaw. However, for simplicity, we don't want to give both roll and yaw input to the plane at the same time. While the plane can be turned by using the rudders, large maneuvers are more efficient by rolling and then pitching. The rudders should only be used for fine adjustments, so we switch between rolling and yawing if the plane's nose is within fine steering angle degrees of the target. Most of the time, our steering needs to roll the plane and then pitch up, so we need to roll until the target is overhead. Then the pitch error will steer the plane towards the target. We use the angle between roll error and the up vector as the roll input. When the target is directly overhead, the roll input is 0. When only fine adjustments are needed, we use the angle between yaw error and the forward vector for the yaw input. Both roll and yaw inputs have a scaling factor which tunes the strength of the input. The pitch, roll, and yaw inputs are combined into a vector 3 target input. The target input is clamped on each axis to limit inputs to the range -1 to 1. We use vector 3.moveTowards to prevent large instantaneous changes to the steering input. The red line shows the position the AI is currently steering towards. With just the simple roll, pitch, and yaw inputs, we have a plane that is capable of chasing the player. Right now, the AI will happily fly into the ground while chasing its target. Some simple logic needs to be added to detect and then avoid the ground. The AI casts a ray along its current velocity vector. If that ray hits terrain, a ground avoidance routine will take over and steer the plane away from the ground. The length of the ray depends on the plane's speed, so the plane will try to avoid the ground from a longer distance at higher speeds. This ray can be rotated slightly downwards to improve ground detection. If the ray hits the terrain, the AI will roll level and pull up as hard as possible. When the ground detection ray no longer hits the terrain, the AI will resume normal flight. This function returns the steering input needed to avoid the ground. The steering vector is set to -1 on the x-axis, which is a maximum pitch up command. The roll axis is calculated to roll the plane level. The AI will now avoid the ground while still chasing the player. While dogfighting, the AI plane will eventually use up its energy and have no speed left to maneuver. When this happens, the AI must recover energy somehow. A human pilot might change their maneuver to take advantage of a gravity assist and gain energy, however, I don't know how to write that. Instead, the logic is simple. The AI will try to keep its speed within a reasonable window. It will increase or decrease throttle when the speed is out of this range. If the speed falls far too low, the AI will start a special energy recovery routine. The AI will roll level, point the nose at the horizon, and fly straight until it regains speed. This leaves the AI vulnerable, allowing the player to get into a better position. This energy management function is not very sophisticated, but it's enough to keep the plane from falling out of the sky. To use the cannon, the AI must get within cannon range and point its nose at the calculated lead point. If it isn't in range, then it will simply point its nose at the target without trying to fire. If it is in range, then the AI waits until the nose is within a small threshold angle of the lead point before firing the cannon. Firing missiles has a range check as well, but there's no need to lead the target plane, since the missile does that automatically. The logic for using weapons is simple, but don't underestimate the AI. It's very much capable of shooting you down. The AI not only needs to be able to use its own weapons, but must also dodge incoming attacks. The steering behavior of the AI is the only logic for dodging cannon fire. The AI is constantly turning to get behind the player, which means it is more or less dodging cannon fire at all times. While there is no special logic for dodging bullets, there is a separate code path for dodging missiles. Missiles fired at long range have plenty of time to correct their course and intercept their target, so the AI can't simply rely on turning towards the enemy like it does with bullets. There's probably a lot of different ways that the AI could dodge missiles. The system I chose is simple. Calculate 4 dodge points above, below, left, and right of the missile. The distance from the missile to the dodge points is the same as the distance from the AI to the missile. Select the dodge point closest to the plane and steer towards it. Since there are multiple dodge points, we want to avoid the problem where the AI switches between 2 dodge points rapidly and ends up flying in a straight line. So we keep track of the last dodge point selected and choose the dodge point closest to it. Then the dodge points are simply fed into the above steering function instead of the target plane's position. The system isn't perfect, but it can dodge missiles reasonably well. The red circles show the dodge points that are available, and the red line shows the selected dodge point. The AI is no longer a cooperative target. It can reliably dodge missiles that are fired from a bad angle, but it can't dodge every missile. The AI right now reacts to the player's movements instantly. This means it's effectively perfect in responding to the player's maneuvers. It's possible to beat this AI since it's still just a handful of simple behaviors, but it's difficult. One simple way to reduce the AI's difficulty is to add a time delay to their maneuvers. If the AI responds to the player's positions from 1 or 2 seconds in the past, it creates opportunities for the player to outmaneuver it. We can implement this by adding a queue for the player's position. The queue items have a timestamp that stores when it was generated. The update loop pops items from the queue after some time has passed. We add a reaction delay variable to control this. However, we don't always want a delay applied to the AI's input. In some cases, like ground avoidance, we want the AI to react instantly. So we add another variable called emergency. This is set to true when the AI needs to avoid the ground, dodge a missile, or recover speed. When it's set, the AI ignores the input queue and reacts to the danger immediately. We add a second, shorter reaction delay for when the player is within close range. This makes the AI have a better reaction time in a dogfight. This is important for responding to the player's movement and especially when it needs to aim its cannon. The reaction delay system is a simple way to make the AI easier to fight. You can change the delay amount to tune the AI's difficulty. All of these systems combine to create an AI that can be surprisingly challenging to fight. The AI will try to line up a shot with its guns and missiles. It will avoid hitting the ground and try to dodge your attacks. It will try to maintain energy, but this leaves it vulnerable. The AI has plenty of limitations though. The ground avoidance is far from perfect, so you can trick the AI into crashing into the ground. The simple steering function and reaction time delay means the AI can be defeated with a rolling scissors fairly easily. You can overcome the AI by outturning it or by draining its energy and forcing it to recover. The AI might do the same to you, so I hope your ground avoidance and energy recovery routines are better than the ones I wrote. You can enable the AI on your plane in the demo by pressing spacebar. This reveals the most glaring flaw. Since the two planes and two AIs are identical, their maneuvers will also be identical. You can easily reach a situation where the two AIs spin endlessly in circles, neither plane ever able to shoot the other down. You can try it right now in the itch.io demo linked in the description. You can also try playing Sinti Combat, which is a game I made based off of these systems. The game is also on itch and there's a video of it on my channel. The code for this project is in the GitHub repo at the tag part 3. The AI we have now is not perfect, but is still capable of winning dogfights. There is clearly room for the AI to be improved, but that is left as an exercise for the reader.